Hi, today we will be learning about probability distributions and hypothesis testing. Consider one coin toss. You can either have a head or a tail as outcome, and the probability of either one is 0.5 or 50%. Extending our single toss to 10 tosses, we might be interested to find the probability of getting 3 or 4 heads. Among the 10 tosses, let us calculate the probability of getting exactly 2 heads. We can write it like this. Heads and tails have a probability of 0.5, and since we observe 2 heads and 8 tails, we get 0.00097. But an additional complication to be considered is the different combinations as shown here. The number of different combinations can be enlisted in 45 different ways using the combinations formula. Finally, in 10 tosses, the probability of getting 2 heads is 0.04. Note that the components that we used in this calculation was the combinations formula, the number of successes, and the number of failures, which will be relevant in a formula that I will share later on. So in 10 trials, we calculated the probability of getting exactly 2 heads, but we can do it for other outcomes. So what is the probability of getting exactly 0 heads? 1 head, getting exactly 2 heads, which we just calculated, getting exactly 3 heads, 4 heads, 5 heads, so on and so forth. When we plot the probability of each outcome, we get a PMF or a probability mass function. The one we are seeing here has a specific name. It is the binomial distribution because there are 2 outcomes and multiple tosses or trials. But what if we want to answer the question like getting the probability of 2 or more heads? One thing to note is that the PMF is the depiction of the underlying data generating mechanism, which is 10 tosses, and we should expect 5 heads maximum number of times, and then 4 or 6, and so on and so forth. So we learned what is a PMF and a binomial distribution in this slide. The formula for binomial distribution is shown on the top right. This is the cumulative mass function. So we wanted to answer the question of getting probability more than 2 heads, 2 or more than 2 heads, and this is the cumulative mass function. Now let us take a look at what is hypothesis testing. As a recap, we acquainted ourselves with the PMF that represents the underlying data generating mechanism of 10 coin tosses. Per this mechanism, we should expect 5 heads maximum number of times, followed by 4 or 6, and then it tapers off in either direction. We now perform a new experiment and we observe 2 heads in our outcome and the associated probability of 0.04. Given that we saw 2 heads, can we assume that the 10 coin toss mechanism still generated our new data? More formally, can we assume that the new experiment follows the same underlying data generating mechanism as the PMF? We call this the null hypothesis, denoted by H0. It is defined as no significant difference hypothesis. The alternative hypothesis would denote that the new experiment does not follow the same distribution. For example, there is some other mechanism where we might see 2 heads most of the times in 10 trials. For example, the coin may be biased. So said another way, what we are really testing is, given that the underlying assumption is true, how likely are we to observe the data that we just saw? These are some definitions that we learned here. Another way to look at p-value is whether it is an indicator of the compatibility between the data that we just saw and the underlying data generating mechanism or the null hypothesis. The larger p-value might be indicative of such, but on the other hand, a smaller p-value would reduce our support for such a conclusion. And thus, as mentioned previously, we might be tempted to negate our assumption since the p-value was small, and it reduces our confidence that the observed data came from the same assumed PMF or the null hypothesis. But wait, that also might be a mistake. We did say in the PMF that 2 heads will occur once in a while, albeit with a low probability. So if that low probability is leading us to negate our assumption, that's a mistake. And we want to avoid such mistakes. Usually, we allow ourselves to make this mistake no more than 5% of the times, denoted by alpha equal to 0.05. I also want to mention that the low probability may not always be an attribute of wrong assumption and correct data. It might also be the case that the incorrectly observed data would lead to a change in the probability value. Consider systematic example. There are two types. The first one is information bias. So if somebody read two heads at the end instead of two tails, that would change the probability because we are now observing 4 heads out of 10. Next, missing data. If we observe or record only 4 outcomes and one of them is head, well, 1 out of 4 is 0.25, and that leads to change in the probability. People have attributed missing data to selection bias. So these type of systematic error can also throw off our probability. I also want to mention that apart from binomial distribution, there are other type of distributions. The distribution plots are shown on the left and the corresponding formulas are shown on the right. The top panel shows the normal distribution, the middle panel shows the t distribution, the bottom panel shows the f distribution. Some clarifications that I would want to make is the p-values in hypothesis testing calculate the probability of observing the value we just got or more extreme. So it's not exactly the probability, it's probability of observing 2 or more heads, for example. So we might have to think in cumulative terms. Also, there are two extremes possible. So one-sided and two-sided hypothesis tests are designed, but that's out of the scope of this video. I have a bonus discussion to make. So we define type 1 error as we want the false positive occurring less than 5% of the times. So out of 100 trials in the future, we could be wrong 5 times. Even if the null is actually true, we would end up rejecting it. But what if we tested hypothesis in tandem 50,000 times? Well, 5% of 50,000 is 2,500 and we would be wrong 2,500 times. The solution to that is to reduce the alpha when doing multiple testing, and I would make a future video on multiple testing. Finally, these are my set of references and the textbook that I used to refer. Please let me know in the comments how you liked the video. Please like, share, and subscribe. Thanks.